Hello everybody and welcome to the sixth session of our electrophysiology trainee workshop. Um, let's start. Today's topic is gonna be machine learning 2, where we're gonna look into a number of different machine learning algorithms, how they work, what's the idea behind separating classes using them, and yeah, I think that's gonna pretty much fill up this entire session. And next session is gonna be about how to when writing code and basically putting all the stuff we have discussed so far into action, how to organize that, how to make sure that's readable, that's maintainable, how to structure that, especially when working together with other people, or then basically having that reviewed by your PI or a postdoc or whoever at some point to make that much easier for them. First I wanted to start with a little comparison of the idea of machine learning and statistics, which could have fit nice into last week's session, but I just thought we're going to include it in this session. In statistics, we usually collect our data, we extract information, model that extracted information, and then we derive some effect size and significance estimation based off of that. And in machine learning, basically we do, interestingly, we basically do the same. We extract data, we acquire data, extract information, and then we model that extracted information. But in this case, we are trying to predict the properties of new data points. Hence, that goes in the direction of the classification problem and stuff alike. So on the left side, we basically have a descriptive analysis. On the right side, we have a predictive analysis. And regarding the pipeline for our machine learning applications so far, we know we have to acquire some data, extract information. The data needs to be modeled, and then we can use that information to predict new properties of new data points. And what we've already discussed so far is selecting different types of models, like unsupervised learning models, supervised learning models, and reinforcement. Talked about reinforcement learning, where we discussed how to train those models, how to select features, why it's advantageous to use cross-validation to evaluate those features, and we also validate to select those features. And we also discussed how to evaluate the model and which metrics may be used for that purpose. And the sole topic of today's lecture is going to be different models for supervised machine learning methods. And one way of doing that is using an LDA. An LDA takes your data set and it tries to find the separation that maximizes the distance between your two data groups, and at the same time minimizes the variance within each class. In this case, we have two classes indicated by the different colors, and although that sounds a little complicated at first, it's actually pretty simple what the LDA does here. If we say the plus signs identify the center, we can say that on the x-axis, this would be the variance of the blue class. On the y-axis, on the x-axis, this would be the variance of the orange class. And as you can see, they are rather broad and they are even intersecting. And if we compare the means of those two classes, you can see that there is some distance between those two means, but our individual variances aren't too great either. And what our LDA node does is it tries to find a separation that optimizes that, basically making this red bar here way larger while making that orange and blue bars way smaller. And an example of that would be to basically also use some information on the y-axis, in this case a little weighted to include more information on the y-axis than the x-axis, and basically create those diagonal lines. With those diagonal lines, we have little different magnitude of variance, meaning that the variance is smaller for the blue group and it's smaller for the orange group as well. And on the when comparing the difference between the means, on the other hand, we get a slightly larger bar here. And that's basically everything our LDA does. It just takes your two classes, and then it looks what's you almost want to say the angle between in the feature space that's gonna optimize that question of what's the angle of broadest difference between those classes, while the variance within those classes remains minimal. And if we compare these two arbitrary examples, we're gonna see that for the first class, where we had the vertical lines, we have higher variability in the classes than with the diagonal lines, being the smaller bars here, but we had a smaller difference between the classes with the vertical lines than with the diagonal lines. And according to the principles of our LDA, that would basically mean that the diagonal separation would be preferable to the one using the vertical lines. And as I said, what the LDA does is it computes that optimal separation by determining the optimal angle to maximize the solution to that problem. And yeah, that's about it in regards to how the LDA works. And for this session, I wanted to concentrate on how those individual algorithms split their data points, much rather than explaining on how that's done mathematically, since that's basically a large abundance of different optimization techniques that one could apply, but 9 out of 10 times those are gonna result in the same outcome in the end. So I think the most important part here is, if you want to select a classifier for supervised machine learning, is to understand what kind of properties this classifier is looking for, then trying to separate your data, so you know whether the classifier, or say the assumption of the classifier, fits the data you want to use with in combination with that classifier. Then, and another method you could use would be a random forest. A random forest is a combination of decision trees, and decision trees are a rather simple concept, and they have the convenient property that you could actually print them out on paper and show them to somebody, and they would immediately understand what the algorithm just did. That's basically how straight simple they are in the end. And with a decision tree, you basically start at the top here, and then you would decide based on criterion XA that a dot belongs into the blue group or in the red group. And XA can be any of those features. For example, we could draw a line in the vertical line here in the bottom left corner, which would mean we take the vertical feature of that 2D example here. And by drawing that line, we are already correctly classifying most of the blue dots, but we are misclassifying 2 of the blue dots. Meaning that if our decision tree said, for example, everything that's left of the red line would go into C1, that's basically what it would do. And then in the next step, it would look whether this separation here can be further enhanced. And that's what basically it would do in that next decision XB here. And then the decision tree has the opportunity to take the same feature again, or it might take any of the other features. And if we look at that bottom left figure, irregardless of whether we draw another horizontal or vertical line in there, there's not going to be a really good way to single out those 2 blue dots, since they are really closely intermingled with the orange dots. So if we look at another dimension, it might, for example, look like that the 2 remaining points correspond to these 2 points here in the bottom right picture. Which means as XB, we could draw this horizontal line here, and then we could correctly classify these 2 blue dots as class 1, whereas all the upper dots would be classified as the orange class. And that only works because in that first step we've already singled out all the other dots. So whenever the decision tree goes deeper and deeper, it only deals with a subset of the original features, meaning it gets easier to basically find a feature that nicely separates your data. But on the other hand, with decision trees, you have the issue that potentially you can go sufficiently deep to have a single feature that separates each data point on its own, which is gonna create you a super nice overfitted model. Overfitted in the sense as in it literally found a feature defining each single data point, which is not what you want, because that's not going to be generalizable. And one way of basically making those decision trees more generalizable and to avoid that overfitting, which naturally has to occur if you just allow the tree to grow deep enough, is to limit the depth of the tree artificially. But then selecting artificially a specific depth isn't ideal either. And another option you could go for is to not make a single decision tree. You could make multiple decision trees. And by making those multiple decision trees, you, as the name already kind of gives away, you're creating a forest of decision trees. And the random part comes in from the fact that whereas we may take like our usual 90 to 10 or 80 to 20 split to train our decision tree, for our random forest we train multiple decision trees, and each of those decision trees gets trained with a different subset of the data. So they basically represent a different subset of the properties from that data. And it also gets a different amount of features available. For example, with that first decision tree, we would give it the top right feature space basically, and the top left feature space, and it could learn from those. It would not get the information from those two feature spaces here on those bottom corners. It would be limited to whatever it could learn from these two, and then would try to take as much information out of that as possible. And the same applies to the other decision trees we are building. And for example, for the second decision tree, we are gonna give it the top right corner and the bottom right corner. And for the last decision tree, we're gonna give it the two left-sided corners. So all of those decision trees try to solve the same problem in the end, but as I already said, they are limited to different subspaces. And we are not only limiting the number of features available to basically increase that generalizability, we are, as I already said, we're also limiting the number of data points. So instead of giving those individual decision trees all data points to learn from, we're only giving them a subset. So some of those data points were grayed out here, meaning they are not provided to these individual decision trees to learn from. And the idea is that if you give each of those decision trees a different subset of data points and a different subset of those feature dimensions available, they're gonna learn different characteristics of your data point, the data you provided them with. But you're not focused on learning one specific pattern. You're trying to basically encapsulate to figure out the pattern of different patterns of separations being available within your data. And by making a really large amount of decision trees, you're gonna end up with some decision trees that are gonna be meaningful, and some decision trees that basically are a combination of features and data points where there's no useful information to be extracted from. But since that's random, and we are gonna make usually the user's gonna make like 2, 3, 5,000 decision trees, one can assume that those basically bad, low-quality decision trees that are not gonna derive any useful patterns for later on are gonna be washed out over time, meaning not washed out over time, average out across the available decision trees, whereas those that actually carry information should more or less always be reliable, meaning that yeah, those unreliable basically, as I said, average out to well, if you had two classes 1 and 0, they would average out to 0.5, whereas the reliables would always go in the direction of the respective point of the class of the point you're trying to classify, meaning that they are gonna pull the weight in the end, the ones that are reliable. And by making enough of them, you're basically guaranteed to have a sufficient amount of them that are being reliable, that carry enough important information for you to go forward, and that actually works out pretty reliable in the end. So that's kind of a really popular approach analyzing data right now, and it's actually a pretty popular approach for analyzing electrophysiological data in particular at the moment. But the drawback from the random forest in comparison to the decision tree is that if you have your decision tree, it's pretty easy to figure out how the decision tree derived its decision, meaning because it stopped at a leaflet that was either class A or class B, class 0 or class 1. With a random forest, it's a little more difficult. You're still when putting your data into the random forest, you're still traversing each of those separate decision trees, but each of that separate decision trees is going to give you their own estimation on whether it's going to be class 0 or it's going to be class 1. So you're going to go you may get different outcomes here. So those decision trees are going to have to make a vote somehow. And usually, popular decision is simply to go with a vote of a majority, meaning that, and that actually comes with two benefits here. Again, the first benefit would be that if you go with the majority vote, you're already washing out again stuff like noise or static in your data, in the feature space and stuff like that, because you're averaging, and that stuff usually, if you're lucky, disappears when averaging. So that's kind of a catch for you when doing that. The other catch is advantage. The other advantage is if you go for the majority vote, you can actually look at how many trees did actually vote for this data point to be class 0 or class 1. And for example, if 80% of your trees said this was to be class 0 and 20% of that said it was to be, the new data point is supposed to be class 1, that would be a different picture than if you had, for example, 60% of your data points saying it was class 0, whereas 40% of your data points said it was class 1. So you're already getting some kind of something that goes in the direction of reliability here when looking into how uniform that vote actually is. Another classifier that I wanted to talk about is the naive Bayes classifier, which is actually a favorite of mine. And I like it because it's that simple in the end. As with all the other classifiers, you start out with your distribution of data points, and this time, instead of trying to maximize the separation, or instead of trying to draw boundaries that maximize or minimize some certain criteria, this approach works differently. For the naive Bayes classifier, we have to tell the classifier what's the distribution of our data. And 9 out of 10 times, the data you're going to be looking into is going to be either Gaussian distributed or perhaps Poisson distributed, and you can tell that to the classifier, and it's going to fit in accordingly in model. And for example, if we fitted a Gaussian model here, we would get some kind of distribution like that for the blue data points, and we would get some kind of that distribution for the orange data points. And then all the naive Bayes classifier does is it looks based on those distributions it derived from the data it was looking into. for any new data point, is it more likely to be part of the orange group, or is it more likely to be part of the blue group? So it's basically using the conditional probability from, or the likelihood from the distribution used to model the data points of the respective classes. So if both classes have a similar variance model behind them, you're going to get a linear classifier. And that's actually what you're going to read in the literature usually, that your naive Bayes classifier is going to default to a linear separation. The part that's usually going to be missed out here is that, as I said, that necessitates that the variance of those two classes is at the very least quite similar. But in practice, that usually is not the case. In practice, usually you have different variances for different classes, especially when looking into the effect of a treatment on electrophysiological data. Usually, you have, like, let's say, a relatively confined default state, and then you apply some treatment and you get super large reactions, small reactions, whatever, but you have a way larger spread. Or it is the other way around, that you have like a relatively spread out default state, you apply some intervention to the patient, and then whatever readings you get are way more confined to a specific spatial area within your feature space. So that assumption of having the same variance behind those two classes doesn't really hold true. And if that's the case, and you would fit your naive Bayes classifier here, you would basically get a separation that would look more or less like that. The naive Bayes classifier still works super effectively. It still is gonna assume that each of those two separate classes can be modeled with a probability distribution. And then it's going to ask again, is it going to be more likely for the data point to be part of the orange group, or it's going to be part of the blue group? And as you can already see, if they are vastly different in terms of their variance, you're not going to end up with a linear separation, but you're much more likely to end up with some kind of U-shaped separation, if it's a two-dimensional feature space. Yeah. Then another technique of separating your data would be to apply a support vector machine. A support vector machine is, when looking into the literature, also it's actually quite diverse. Sometimes it's identified as a linear classifier, and sometimes it's identified as a nonlinear classifier. And we're gonna come to that confusion in a couple of seconds. What your support vector machine does is actually more or less similar to how the LDA worked back at the start of the presentation. Your support vector machine looks for those two data points that are closest to each other, and then tries to separate to maximize the spread in between those data points. And so you're still it tries to basically through that way it tries to identify where best to lie that separation line. So if we looked at this example here, we would get one line here which would correspond to this orange dot here, and we could get one line here which would correspond to this blue dot here, and that would be our separation line. And as you can see, that separation, those two separation cell lines are purely defined by this orange line here and that blue line here. Meaning, whatever all those orange dots in the back here do and those blue dots in the back here do is totally irrelevant for that kind of separation. So it's only gonna take those 2 points in account. So if you had like way more orange dots back here, way more blue dots back here, would not matter at all. Only if they are dots that are closer to, more close to one another, you would have to shift those lines. Anyway, as I said, the SVM tries to then to maximize to basically again find an angle in your feature space that maximizes the separation between those two support vectors indicated by the indicated by the yellow squares. And but it's a little quick. That usually works out relatively nice, but then you can also use your support vector machine to classify nonlinear data. And that's usually done with what's called in the literature using a kernel, or sometimes referred to as the kernel trick. And what you're basically doing is you're bending that line of separation, meaning that you're still having your two support vectors, but this time you're not applying linear separation anymore. You're applying whatever kernel function you specified. Usually that's something some curved function, but in the end it could be arbitrary. You can define whatever function you want for that to be used. And that's already kind of the drawback of the approach. With this example, as a human, I can usually pretty easily see that I fit a nice curved line in here, and that's gonna fit way better than fitting a straight line in here. The issue is if you have your feature space and you have like your 80-dimensional feature space, not gonna be as easy to identify what kind of function is gonna be the ideal kernel function to separate your data, and that's kind of wink back to last week's lecture when we talked about tuning hyperparameters of classifiers. Using different kernel functions, for example, would be tuning a hyperparameter of the SVM. So you could evaluate a number of different functions on all the feature spaces available and basically select the one which fits best. And yeah. Anyway, if you applied your nonlinear kernel here, it would still try to find those 2 points where the difference between the classes can be maximized. And the kind of confusion between whether the SVM is a linear or nonlinear approach comes from the fact that by applying this kernel here, you're basically bending this line here, making it into something obviously nonlinear. But if you would apply the inverse of that separation line to your data, your SVM would again be perfectly linear. You're just doing it the other way around, basically. What's usually a nice example to explain the advantages of the SVM is this one here, where we have the blue dots in the middle and we have the orange dots on the outside. And then we can say if we apply the right kernel function with our SVM is gonna create these 2 lines here, identified by these 2 points, and it's gonna separate out the maximum between those 2 points. But that's kind of goes in the same direction as previously. If I already know that my data is gonna be distributed like that, I can apply some kind of inverse transformation to make that into something that's linear separable. So when applying your SVM, you usually want to try a number of different kernel functions to see which one is gonna fit best. Since with that, let's say 80-dimensional or whatever feature space, you're not gonna know from the back of your head, and there's no way of basically to visualize that meaningfully to know what kernel function to pick from. And so far, we only have talked about, in terms of SVM, we've talked about the hard margin SVM. Hard margin means basically that, as you can see, that there's not for the hard margin SVM, there's not a single data point. That's bad. There's not a single data point to be allowed within that space. And the opposite would be a soft margin SVM. With the soft margin SVM, we still have our support vectors, but we allow for some data points to be within the separation area or even on the other side of the separation area. And the reason for that is that 9 out of 10 times your data is not going to be perfectly separable. And with the soft margin approach, you are compensating to that for that to some degree. And you also want to avoid overfitting. Theoretically, you could fit a line through here that like snakes through those data points, catching all of them on the right side, but you really wouldn't want to do that, because by doing that you would be so strongly focused on the highly specific pattern you just observed within your training data that would be not generalizable to anything, basically. Yeah, and by loosening that restriction of having no point on the wrong side of that separation line, having no point in the middle, your SVM becomes a little bit more generalizable and easier to adapt in your data. Yeah. And then another totally different approach to what we've heard so far is k-nearest neighbors. K-nearest neighbors, well, for all the other methods, you so far you had to learn a specific pattern. With the decision tree, you had to learn basically which features to navigate and where to make a line to identify your classes. With the LDA, you had to identify the perfect angle to separate your data. With the SVM, you had to identify the support vectors and also you had to identify the support vectors. With the naive Bayes classifier, you had to learn the distribution from your data, but with the k-nearest neighbors approach, you're actively not really learning something. Technically, when applying that, you still have to fit your data to a model, but this time you're not training an intelligence, you're just creating a grid which is gonna make it later on easier to determine what's the closest neighbor of a specific data point, since otherwise you would always have to compare each data point to every data point available to collect to know which are the n closest neighbors. And that's what the k-nearest neighbor algorithm does. If we want to classify that gray point here, we are looking at a specific neighborhood of this point, and we have to define this neighborhood either by size or we have to define it by number of points in that neighborhood. And to get that quickly and in an efficient way, it's usually highly effective to have a grid-like structure in the memory of the PC to quickly access that. For example, if I wanted to identify this gray point here, and I would have my 2D grid-like structure of this two-dimensional feature space here, I could already rule out this point on the top right, that orange point here on the top right. I can already rule out those points here, since if I quite literally applied grid-like structure here, I know which points are going to be close to that point and which points are going to be rather far away. And that's going to speed up that process tremendously, and that's what you're learning when you're training your k-NIGHT classifier. But again, let's say we select our neighborhood by number of data points, in this case 5, and if we then ask the k-nearest neighbor algorithm what kind of class this is, it makes usually a majority vote based on the data points in its vicinity. And that's also the reason why you want to go for an unequal number. You want to get an unequal vote, otherwise you're gonna get, like, with an equal number you may get 4 votes, which may be like 2 for the blue class, 2 for the orange class, and you're back to square one because you don't know which one is more reliable than the other one. So if we make our majority vote here, we have 3 votes for the orange class, we have 2 votes for the blue class, so the new point is gonna be orange. And that's basically all it does. And that also works out for that example that we used the M for, where we had that circular structure. We can identify that this point is going to be likely a blue one, since we have 3 in the since if we take the neighborhood of 5, we have 3 blue dots, we have 2 red dots, orange dots. That's going to be blue. If we take that one, we also get its neighborhood of this time all orange ones. And as you can see, as we just define the number of neighbors, the radius around that point is scaling dynamically, which is really convenient, which is why it's easier to go for a number of neighbors than for a certain radius for the neighborhood. Yeah, and then I have this beautiful example here, which you could not separate with an, at least in this feature space here, you could not separate with you could not separate that with an SVM or naive base classifier. You might be able to separate that with a random forest, but you can also separate this here with the KNN classifier. For example, if you want to know what this gray dot belongs to here, gonna do the neighborhood thing again, it's gonna be orange. This dot here, gonna do the neighborhood thing, and this dot's gonna be blue. And yeah, then I got one more example. Okay, and the k-nearest neighbor approach is usually really powerful, but it really requires a small dimensionality. If you have a really high dimensional feature space that is sparsely populated, that approach is not going to work really good for you. You want to have the opposite. You want to have low dimensional feature space, and you want for that to be really plentifully populated. It's kind of a drawbacks of the approach in terms of what it needs. On the other hand, in comparison to literally all the other approaches we've looked so far into, this approach is way more robust in terms of its susceptibility towards outlier and the like. Then I think we have the last classifier for today's lecture, which is artificial neuronal networks. And although they were originally developed to model how actual neurons work, nowadays we know that actual neurons are way more complicated, and artificial neural networks are really a cross simplification of that. And you're gonna see that in a couple of seconds. Let's say we have our 8 dimensional feature space here again, visualized in dimensions of 2. And last time we used the random forest to determine what a new data point belongs to, how to separate between those classes. And with the neuronal network, we kind of do something similar like with our decision tree. The simplest model of a neuronal network would be a perceptron, which gains input from those individual features here. That gets multiplied with a specific weight, which usually ranges from 0 to 1. And then that neuron here decides that it's going to output. And it can only output a 0 or a 1. There's nothing in between usually. And that's the simplest model. And if you concatenate those neurons, you're going to end up with a structure like that, which is going to look like our decision tree, but from the top, basically. Yeah. And then with those individual nodes, a little further, it's going to be easier than that. Yeah. So while for the decision tree we allowed it to learn from all inputs at the same time, we can, for example, for our neuronal networks say that at specific height levels, it's only allowed to incorporate specific information. And one way of doing that would be like if we had a neural network structured like the model on the left side here, we could say that each 2-dimensional feature space would be allowed to contribute to the next layer. And if we took, for example, the vertical feature of this feature space here, we could separate the dots on the left and the right side. Here we took the horizontal one, and then we could combine those two features. And we would get values for those, and we can separate that again as the feature space of XAB. We do the same on the right side, and we can do that again, and by iteratively evaluating again and again and again what some kind of higher order features of the original features, we are gonna get close, hopefully closer and closer to the classification we want to have in the end. Yeah. And while that might sound simple if we have a model like that, with a neuronal network, you usually don't have that few connections. That's gross simplification on my end here to explain a little on how they would work. You actually usually have most of those layers as dense layers, meaning that every input neuron is connected to every neuron on the next layer. And that would basically look like that. I gave those here individual colors to make it easier for you to follow those lines. But it would basically mean that whatever information goes into the pink neuron here on the left side goes into might potentially go into each of those 3 neurons on the subsequent layer, and then so on. And here on those connection points, as already explained, that information gets weight. So we are gonna have the pink information times a factor, the yellow information times a factor, the orange information times a factor, and the teal information times a factor. That gets summed up, and then we are gonna ask a question whether that exceeds a certain threshold or not. If that exceeds a certain threshold, then the red neuron is gonna fire. If it does not, red neuron is not gonna fire. And yeah, when training your artificial neuronal network, what you're in the end training is the weights at those individual dot connections here. You're training how much the information of the red neuron, for example, would impact this neuron here. You're training how much the red neuron gets impacted by information supplied to it from the pink neuron, and so on. And that's what you're learning. And then modeling those, which is way more complicated than doing all of those other approaches. You're not restricted to a specific rigid model like with many of those other classifiers where you had like 1 or 2 hyperparameters. With an SVM, you're literally doing a jigsaw puzzle, puzzling together individual components and later on calibrating them through learning in hopes of that whatever you puzzle together and got calibrated later on is able to determine a specific pattern within your data. And going for dense layers is one option. The other option is, where I kind of grabbed the example from, would be to go for convolution layers. Convolution layers usually only allow input from neighboring neurons, and they are really common if you do if you process imaging information. Because if you compare 2 pixels in imaging information, you're basically asking whether you have an edge at a certain pixel. And that information could already be interpreted as a higher order feature. And so what kind of layers you want to use really depends on the data you want to analyze. And if you want to use a neuronal network to analyze that data, you have to select as I said, what layers you're going to use. You're going to have to select what activation function, which is something I've not yet discussed in the scope of that, since it would simply go way beyond the scope of this workshop. You would have to an activation function. You have to determine a large number of further parameters, which all go into the modeling aspect. You have to determine, for example, how many neurons you have in each layer. In these two examples, I have a steadily decreasing number of neurons, but you not necessarily have to do that. You can have your model shrinking in size, growing in size, and shrinking in size as arbitrarily as you want in the end. The question is whether that's going to be beneficial for you or not. And while the number of hyperparameters was reasonable if you did your SVM or your naive Bayes classifier, with your neuronal network, the number of hyperparameters is basically the different types of neuronal models you could use to evaluate your data, and that number is so large that you cannot test all of them anymore. Hence, you have to you have to have some idea of what kind of model you're going to go for. You have to have some knowledge about some intrinsic knowledge about the property of your data to leverage your leverage an artificial neural network for data analysis. So in the end, just to summarize that a little, you have to define the individual layers, how many neurons are in those layers, and you have to define what kind of connection between those layers is possible, indicated by those white bars here. And in my experience, if you do a neuronal network, you're gonna invest a pretty significant amount of time into configuring the thing correctly. And if you have like a simple problem, you usually fare better with applying a simple approach like the naive Bayes classifier. If you have really if you have like a somewhat nonlinear problem, 9 out of 10 times you're still gonna fare pretty good with a linear approach. So the problems that actually necessitate a neuronal network are the really complicated ones, where you can leverage the advantage from those different neuronal layers. And you have, as I said, you have to know what properties your data have, and whether your data actually, whether the properties of your data can actually be leveraged by the different layers you can use in your neuronal network. The example of that would have been, for example, that in the convolutional neuronal network, you can leverage that if you have imaging information, that the difference of two neighboring pixels is going to indicate an edge. If you have electrophysiological information, it's gonna get a little bit more difficult, because even if you calculated the difference between this sample and the next two neighboring EEG channels, that wouldn't be it's more difficult to grasp whether to have an idea from the start whether your artificial neuronal network is going to profit from that or not. So usually I'd recommend to start with a simple approach first, and only to go to the more complicated ones if it's actually necessary from your data. Yeah, and that's it so far about that session from the machine learning 2. And I hope I could explain a couple of different machine learning methods to you, to basically bring a little bit closer to. I think the most important part of the machine learning stuff is to, as I already said in the beginning, to actually know how those individual models split your data, or at least how they try to split your data. And then you're gonna see pretty quickly that, for example, if you have K and N, where you're gonna look for the K nearest neighbors, if you have a sparse feature space and you have really high dimension of features, it's gonna be pretty it's not going to be difficult to understand why this is likely not the ideal approach. Or if you have like super nonlinear distributed data, where we had basically the blue circle engulfed in or surrounded by the orange circle, you would not be able to do an LDA here and get any meaningful insight. But yeah, so I think that's I hope that's something I yeah managed to explain in this session. And next session is going to be about programming. So as I said again at the beginning, that's going to focus on how you should structure your work, how you should structure your workflow, and that's going to help you with reducing the amount of mistakes you make along the line, facilitating your cooperation with cooperating with others, making code revisions easier, and the nastiest thing that basically can happen to you throughout your career is you doing an analysis, spending like half a year on that, having your code written, looks all fine, you have super nice results, you're gonna like have written a nice paper on that, it's gonna be super highly published, and then this later on some person goes through your code and says there's some bug here and here, which means you have to rerun your code, and if you're unlucky, results disappear. So that's what we are going to discuss next session, and I hope to see all of you again then. Thanks for your attention, and if you have any questions, please let me know.